Okay, so welcome all to the live session for the challenge remarks of the Continual Learning in Computer Vision workshop at CVPR 2020. My name is Vincent Solomonaco, and together with Roger Shi from Intel Labs, we are going to present the results of the challenge, as well as give the awards to the four best performing teams with respect to the four different tracks we had in the challenge. Then we will let the four best performing teams to have a quick presentation of 5 minutes so that all the people joining in today can see how they achieved the, let's say, their score in the ranking, in the final ranking. So first of all, what were the challenge objectives? So first of all, we like to propose the first Continual Learning challenge ever organized at CVPR, and so bear with us with possible mistakes that we introduced and possible misleading instructions because it was the first experience also for us. And the idea was also to scale continual learning approaches to natural images and possibly video benchmarks. And this is why instead of using simple data sets such as a MNIST or CIFAR, we decided to opt for CLVision, which is, we believe, a reasonable trade-off between, easy to manage and for prototyping benchmark and, a benchmark that can be useful to address natural images and real-world applications. In fact, the objective was also to assess the feasibility of a continual learning approach in a real-world computer vision application context, in this case, object recognition, continual object recognition. And also to invite the community to work on solutions that could generalize over multiple continual learning protocols and settings, and be robust, and generalize over those. And then also the last important point and objective of this challenge was to provide the first opportunity of a comprehensive evaluation on a shared hardware platform for a fair comparison, introducing different metrics, not just forgetting on the accuracy metric, but also efficiency metrics we regard as very important for assessing continual learning algorithms. So again, if you're not familiar with Code50, you can check these out at the official website, vilomonaco.github.io/Code50. And but by now you should be able to recognize its main features. I think that Davide also presented it in his invited talk, and many other strategies in this workshop tried their algorithms on this dataset. Then based on Code50, we defined 4 different tracks. So they're not in order of complexity, as we will see later on, but they are different protocols that we think are useful to assess continual learning strategies. So the first one is the new instances track, in which we try to assess the performance of a continual learning model in a scenario where in each incremental batch you encounter new examples, but of classes you have already seen before. And so in this case, we are a single task, not multiple tasks, and we try to improve the performance of our model over time, just with new examples from different distributions. And the second track is about multitask learning, let's say, continual learning with new classes that we encounter for each of the incremental batch. And in this case, we have also access to the task, let's say, information label, both during train and test. And then the third track is about the new instances and classes scenario, in which we have a large number of small incremental badges containing very few images of just one class. And of course, in these badges, you can find new instances of classes you have already seen before, but also examples of classes you have never encountered before. And this is, we believe, one of the most interesting and natural settings you will find in many, especially continual learning at the edge applications. And then the most difficult track was instead the ones combining a solution that could work on these 3 different tasks altogether. So thanks to the sponsor of Intel Labs China, we have been able to give to the 4 best performing teams 4 different awards, monetary awards. So we decided for the old track to give $800, for the other 3 tracks $500, as we believe, again, that the old track is the most difficult to achieve. So I think that, yeah, maybe I can clarify the metrics, and I leave Roger to give the awards. So for the metrics, we decided to have the basic, let's say, final accuracy on the test set at the end of the world training procedure, but also take into account the average accuracy on the validation set over time. Then somehow a metric assessing the computational efficiency of our strategies, the total training and test time, running time of the algorithm, and then the RAM and disk usage as well. And here, sorry, there is a mistake in the last number here. Oh, sorry. But essentially, these numbers that you can see in the parentheses are the weight that sum to 1. That weighs somehow the importance of each of these metrics in the final, let's say, continual learning score that is going to rank each of the participants. So for the final accuracy on the test set, it's 0.3. For the average accuracy over time, it's 0.1. So let's say 0.4 is the weight for the test accuracy, sorry, the accuracy. And then the other one are for the efficiency of the strategy, with 0.15 for the time, and then 0.125 for the RAM usage, and 0.125, sorry, this is a mistake, for the disk usage. Okay, so these instead are the numbers for the challenge. So we have seen 79 teams that registered for the challenge, and then of those we selected just the first 11 teams that participated to the finals, and for a total of 46 people that joined the finals, and let's say an average team members composition of 4. So these are the 11 finalists that in the end were selected for the finals. Oranzu, ICT, VIPL, GBB, Jodelet, Jun Tutong, Mr. Grandy, Noobmaster, Sainu, Sony, UTLG, YC 14,600. So I would say congratulations for being part of the 11 teams that arrived here. Now I think I can let Roger speaks and give the awards for the 4 different tracks. So let me switch up my sharing, and Roger, if you want, you can share your screen.
Yeah, thank you. Okay, so it's right for my screen.
Yes, we can see it and we can hear you well.
Okay, so as Vincent you introduced, all the challenge prizes are divided into 4 different tracks. The first track is about learning the new instance, and the winner is yes, the ICT VIPL teams. Thanks.
Congratulations.
Thank you. Thanks. So congratulations to the team. So the team will receive $500, and the second track, the winner is in the scenario of multitask and learning the new classes. The winner is YC 14600, and the same. Congratulations to the teams. And the third track is learning the mixture of the novel instance and classes. The team is Jod Late, and also will receive $500. Congratulations.
Congratulations.
And also for the final track, we evaluate based on the average score of all the 3 tracks mentioned above, and the winner is UTLG teams. Congratulations.
Congratulations, guys.
And besides the best paper award announced at the closing remarks, we will also announce the second best paper winner in our workshop. The paper is called The Dropout as an Implicit Gating Mechanism for Continual Learning. And the winners will win a signed copy of second edition of the book, Lifelong Machine Learning. Congratulations for the teams and the authors. Yeah. So Vincenzo.
Thank you so much. Thank you so much, Roger, and congratulations again for to the winning teams. What we will do is to create a certificate for all the finalists that I will give you later on at the end of the workshop, and also we will upload your report on the website, and if you want as well your presentation. So let me start sharing again my screen and continue with the challenge remarks and to see the actual results. Okay. Okay, so these are the results for the NI tracks. Of course, you will be able to check the results later on. We don't have all the time to look at all these numbers. I will try to summarize them at the end, but essentially you will be able to look at them on our website. So here you can see the 11 teams, but also in orange, 3 baselines that I added to understand really the quality of these solutions. So the first one is the rehearsal baseline, in which what we do is just add 20 images for each batch or task, so that we have an external memory, ever-growing memory from which we can rehearse. And these are the results for the NAI strategy, for the NAI track, sorry. And then we have the naive baseline, that essentially is just fine-tuning the model over time with a new batch of data. And the R1 strategy that I think David introduced in his invited talk, which is another baseline that has been already proved to be successful on Core 50. And in this case is not calibrated in terms of hyperparameters, so it's just a fixed hyperparameter, let's say, the hyperparameters are not chosen to and optimized for each track, but are rather the same hyperparameters across all the different tracks. So in this case, the UTLG teams is the best performing team. So you can see it, and the ranking is actually respecting the CL score that you can see in the last column here. But essentially, what you can see is that the UTLG teams has been able to achieve impressive, I would say, accuracy performance at the end of the training. And this is, of course, the main drive to the CL score. I remember you that essentially the accuracy at the end of the training procedure is counting like almost half of the entire score. And I would like also to congratulate the YC 14,600 team, as well as the ICT VIPL team that performed well in this track. Other thing maybe to notice is that as for the other tracks, most of the teams decided not to store the replay patterns into the disk, but rather decided to maintain them on the RAM, and so to somehow reduce, I would say, the runtime of the strategy. Also because essentially we run the algorithms on an hardware with 32 gigabytes on RAM, and somehow it was possible to store all the necessary replay examples into the RAM. All right, so then for the MT&NC track, we can see that the best performing teams have UTLG, it's YC 14,600, and Sony. With that, I would say, even those cases, impressive results in terms of accuracy. But maybe, yeah, not that contained memory consumption. Here we are looking, sorry, I didn't mention it before and didn't put it in the headline, but essentially all these memory usage, are the unit here is the megabytes. So we are talking about 10 gigabytes for the first strategy here, 13 gigabytes, 15, and so on. So, it seems that you can achieve impressive results in terms of accuracy for these, I would say, simple tasks, such as object recognition on this benchmark. But it's difficult to think of these strategies as working in an embedded device, I would say. Then for the NIC track, I would say one of the most difficult tracks in the challenge. And you can notice that also by the fact that many teams didn't attempt to solve this task as well, this track as well. We can again see that the UTLG teams is one of the best performing teams, followed by Codalab and then ECT VIPL. That again, is one of the first teams that decided to move to have the memory examples into the database. So this is the study ranking for the old track. And in this case, we can see the average essentially of what we have seen before in the previous tables. And in this case, again, the first best performing team is UTLG, the second one is Codalab, and the third one is YC 14,600. So what we can get from, let's say, these results. First of all, that in terms of difficulty, the multitask new classes track was the easiest one with an average accuracy at the end of the training procedure of 85%, followed by the NI track with an average accuracy of 82, and NIC with an average accuracy of 62. And somehow this was this is understandable because of the additional supervised signal that you have in the multitask and see the case. Then something interesting to note is that for this challenge, essentially all the teams started with a pre-trained model, used a pre-trained model on ImageNet. 90% of the teams used a rehearsal strategy, proving that if you want to solve a practical task, today you want to use a rehearsal, a replay-based strategy. And then 45% of the teams use a regularization approach as well. So it means that many teams also try to combine the regularization with a memory replay approach. And then 27% of the teams use an architectural approach. So another interesting point to make here is that the average maximum memory size, so the maximum memory that a team would employ for each of the tracks, the average of these is 26K for all the teams and all the tracks. And this is 21% of the entire Core 50 training set. So this is an interesting number here, because it seems that, I mean, it's true that you can reach impressive accuracy results, but at the same time, we are still using a lot of past training data that we encountered before. So this is why I will point this out in the next slide how we can improve on this. Another thing to notice is that almost all the teams propose different algorithms and hyperparameters for each of the tracks. So it seems that it's still difficult to find a single continual learning strategy that can work well on different protocols. And it seems that many strategies that have been proposed have been carefully tuned to satisfy the specific settings and protocols. So what I'm trying to say is that it's difficult nowadays to come up with practical solutions to continual learning that work out of the box without a specific parameterization, a general and agnostic parameterization with respect to the task we would like to solve. So in terms of future improvements for the next edition of the challenge, what we would like to do is to disincentivize the over-engineered solutions, so we have seen in this workshop as well. We will fix possibly the data loading process that is not really relevant for the continual learning aspects. Then we will, for example, count the number of replay patterns rather than pure, metrics taking into account the memory, because you can find many ways of reducing the memory consumption without necessarily reducing the number of replay patterns. And then something we would like to consider is to automate the evaluation completely. So with a remote Docker evaluation that is working also during the preselection phase, and also to compute the metrics not within the process itself, as you being forced to do, but computing the metrics in the Docker host. And then the last point is try to incentivize the focus on pure continual learning strategies rather than deep learning, let's say tricks, like data augmentation, stuff like that. So trying to incentivize the use of non-pre-trained models, maybe smaller size models with faster maybe inference time, and then also using a single code base and single hyperparameters for different tracks, and also for example increase the the weight for the memory usage metrics, number of patterns, and so on and so forth. So this was essentially the summary of the challenge. I hope you all like to be part of the challenge and to participate in the challenge. Of course, any feedback is very more than welcome to improve based on your suggestions. So feel free to contact me at vincenzo.lomonaco@unibo.it if you want to get in touch, or just on Slack. I would let now the UTLG team present their own approach for 5 minutes.
So can I share my screen?
Yes, of course. So I will stop recording here and you can share your screen, right? You should be able to do so. Okay, great.
You can see my screen, right?
Yes, yes.
Okay. So, okay, yeah. So hi, everyone. Thank you. Firstly, thank you so much for organizing the event and the challenge. So my name is Zita. So I am a master's student from the University of Toronto. And it's my honor to talk about our approach here. And in our team, we also have Hyun-Woo Kim from LG Science Park, Juwan Jong, and Scott Sunner from the University of Toronto. So, yep, the challenge is based on the Core 50 dataset, and with 3 tracks. I think the challenger have already explained it, so I will move to the next slide to talk about the first track. For the multitask new classes track, 50 classes are split into 9 destroy tasks, and most importantly, the task label is given in both training and testing time. So based on this property, our approach is extremely simple. Just fine-tune a fresh training model for each task to prevent the interference. So surprisingly, it works pretty well. So, and for the next track is the new instances. For this one, task label is not given, and there are 8 tasks, and each one contains the new instances for the same 50 classes. And our approach is also very simple, just pure experience replay. So for people who are not familiar with that, we have memory buffer to store the sample from previous task, and we only use one single pre-trained model for all tasks. And so when we see the first task, we fine-tune the model with the samples in this task, and then by the end, we will store some of the samples into the memory buffer. So when we see the second task, we select some of the samples from the memory and concatenate it with the current task. And then we perform the training. And same as before, we restore some of the sample from this task into the memory buffer. And we will repeat this step until we see all the tasks. So when we finish training all the tasks and before we go to the final evaluation, we actually select some of the sample from the memory buffer, and then to perform another round of training. So this is like before the final exam, I will review some of the notes to remind myself of all the knowledge I have learned. So we basically do the same thing here. We ask the model to review some of the samples from the memory buffer. So this is the basic idea of our approach. So for new instances and new classes, there are more tasks, and each task only contains 300 images, and the task label is not given as well. So we basically use the same method as the new instances, except for the number of sample retrieved from the memory and the number of samples stored in the memory from each task are different. And as for the architecture, we use a pre-trained DenseNet 161 for all scenario, and we freeze the first 2 blocks of this network and only tune the other 2 blocks. And we perform some pre-processing. I think the most important here for us is the center crop. We center crop both training and testing images with 100 by 100 window to avoid effect of the background. And after that, we will resize all the images to 224 by 224 to match the pre-trained models in precise. And of course, we use data augmentation to improve the generalization of the model. So these are the basic of our approaches to the challenge. They are very simple, and I think I'm pretty lucky to get into the top 3. And then thank you so much. And if you have any question, you can contact me through this email. Yeah.
Of course, thank you so much, Zeta, for the presentation. Yeah, I think you nailed pretty much most of the tricks with which you could achieve incredible, interesting performance with just replay, let's say, strategy, right?
Okay, thank you. So how can I stop sharing?
You should be able to find a red button to end the screening here on top of your screen, I guess.
Okay, I can. So I just quit the Zoom. Left me.
Oh. Okay. So now we will hear from the ICT VIPL team.
Okay, I will share my screen. Maybe. Can you see my screen?
Yes.
Okay. Hello, everyone. I'm Chen He from the Institute of Computing Technology, Chinese Academy of Sciences, and I'll show the approach of our team. Since we take part in all the 3 tracks, I'll introduce all of them. First, I'll show the general techniques that are effective for all tracks. As for performance, yes, deeper network, the deeper network, the better, and more complex data augmentation, the better. And we also found that the original Core 50 dataset has an image of 128 by 128, but the pre-trained model used in the official code is trained with images of 224 by 224. So we think that using the resizing technique can encourage more knowledge transfer from the pre-trained model. We also use an exemplar memory, which is an effective way to alleviate the catastrophe forgetting in incremental learning. And here are the results of using different hyperparameters. And these numbers are all acquired in NIC track. And we can see that using more complex data augmentation, the better, and the deeper network, the better. But there's a trade-off between the memory usage and the performance. So we use ResNet 50 at the end. And the input size, already mentioned before, using the resizing technique is much better. And for the exemplar selection, we found that random selection is good enough. Sorry about this. And for the numbers of exemplars for each step, generally the more the better, but it is also a trade-off between the performance and the memory usage. And we add 5 exemplars for each step in NIC track. And here are the track-specific settings, which can also be found in our paper, and I don't spend too much time here. And here it is a pipeline for NI and NIC. When the new increment arrives, we select and store some only a few samples into the exemplar memory. Then we combine the new samples and old exemplars, create a new training set. And finally, it is just like conventional CNN training. One thing to note that for NIC, we add an additional step, which is to divide the softmax output by the prior probability of each class, estimated by the ratio of training samples of each class. And then we predict the label with the highest score. It is a simple strategy to tackle the class imbalance problem. As for multitask NC, we found that it is an incremental version of multitask learning. So we disentangle the representation learning and classifier learning, and empirically divide the training step into 4 small steps. We take, assuming that we are going to learn task T, for example, first we will train the head T using examples of task T. Then we create a balanced training set and store these exemplars. And third, we fine-tune the feature extractor using all exemplars. And finally, we fine-tune each head with corresponding exemplars. And here are the results on the Codalab leaderboard. We get a very high accuracy, but notice that the numbers of space and time on Codalab are inaccurate, and the final Docker evaluation results from the organizers are more authentic. We also did further analysis on these tracks. For example, NIC track is the most difficult one, and we draw the confusion matrix. And we found that there are many block-wise patterns above, indicating that confusion mainly come from instances from the same category, like different types of adapters, mobile phone, etc. And we also show the failure cases, some cases that are really difficult. For example, there are cases that are difficult under certain shooting angles, like confused with instances of the same class. For example, this one shows the bottom view of a can. You can hardly tell which can it is. And there are several different kinds of failure cases. I don't spend too much time on it. So I give some suggestions on further improvements. For example, we can devise a more principled way to select exemplars. For example, automatically reserve more exemplars for harder cases. And we can use some fine-grained classification features like second-order pooling, attention, 3D information, etc., to help us solve that the problem mentioned in the confusion matrix. And third, we can use some temporal information since the challenge is more oriented for video object recognition. And that's all for my presentation. Thank you.
Thank you so much. Thank you so much, Shen, for your presentation. I think we are kind of running out of time, so let's move quickly ahead with the next team, which is going to be YC 14600.
Okay, I'll share my screen.
Yes, thanks.
Can you see it?
Yes, please go ahead.
Okay, so our method is called, we are from University of Bristol and Amazon. Our method called discriminative representation loss for continual learning. And this core idea is, the core idea is based on the gradient-based approaches using episodic memories. If you have ever heard of Gen and AGen, they basically using the samples in the episodic memory to generate some gradients, and the inner product of the gradients with the current sample from the new data. It's like decide the conflict degree of the two samples. If the inner product is negative, which means the two gradients conflict to each other, they are in different directions. And so those methods focusing on pushing the inner product to be a non-negative value. But in most of those methods, they reproject the gradient during the training time, so it's kind of expensive in computational cost. And by some empirical study, we found that the inner product of gradients is actually correlated with the inner product of the representations. So we used extra loss to replace the reprojection of the gradient, which we called it discriminative representation loss. The idea is simple. It's like to make two samples from different classes less similar, and two samples from the same class more similar. And you can find the loss function is kind of linear, just to the inner product of matrix. So the computational cost is relatively low. And it's kind of the thing of this method. And this is some results after we train the model by the DRL, and we compare it without this loss function. And we can see that the similarity between gradients has been pushed to the center of 0, and the representations has been pushed to the other way around, like two different classes samples become less similar. And that's mean we achieved the same purpose as Gen and Agen, but with much lower computational cost. Basically, this is the core idea of our method, and we also use the pre-trained model, which is ResNest 50, and also it's based on experience replay, but it's kind of simple. We didn't use the pre-processing of images. You can find all the details in our paper, and there are some extra results. We're comparing with some benchmark methods. We will put a full paper on archive soon, so if you are interested, just let me know. So basically, this is our approach. Thank you very much.
Thank you so much, you. Well, let's go ahead with the next presentation, the last one for this session from Codalab. Sorry, it's a video, so he cannot be here, so I will show you the video. So then I've also noticed that there are some people here that are waiting for the Q&A session. Just to advise you that we are running 5 minutes late. So stay with us and wait with us, and then we will start directly in this same Zoom room with the Q&A session for the invited folks. All right, so let's see the video from Codalab that I have here ready for you. Can you see my screen? And then the presentation?
Yes, we can.
Yes.
Okay,
Yep.
Let's see.
I'm Jodelais Quentin from Tokyo Institute of
Can you hear me as
Technology,
well?
and I will briefly present
Yes.
our work for the challenge of the CVPR 2020 workshop on continual learning in computer vision. This work has been conducted under the supervision of Professor Tsuyoshi Murata and Vincent Ripon. The objective of the challenge was to create a model which is able to achieve the highest possible accuracy on 3 distinct continual learning scenarios: the new instances scenario, the multitask new classes scenario, and the new instances and classes scenario. Additionally, the memory and computational complexity of the model were also considered and should be limited. Our proposed approach consists of a pre-trained backbone used at the feature extractor, followed by a logistic regression, which is combined with a reservoir memory used for rehearsal in order to mitigate catastrophic forgetting. So, at each step of the training procedure, each new element is saved in the reservoir memory if the later is not full. Otherwise, new element has a probability m over n to take the place of an old element in the memory, where m is the size of the memory and n is the total number of previously seen elements. In order to have a fast training algorithm, we choose an online approach where each data is only seen once. At each step of the training procedure, half of the batch is composed of new unseen elements, and the other half is composed of elements randomly sampled from the memory. Our objective for the challenge was to minimize as much as possible both the memory and computational complexity of our solution. Therefore, we decided to not fine-tune the backbone and to store the feature vector in the memory instead of the whole images. The first design choice of our solution is the selection of the backbone neural network. It is the most important choice because it will mostly define both the accuracy and the complexity of our solution. We chose ResNet for the architecture and selected two training procedures among the ones we studied: the reference training procedure using ImageNet dataset and the semi-weekly supervised learning procedure proposed by Facebook AI. This novel training procedure allows a notable increase of the accuracy without any modification of the architecture. The second design choice is the selection of the size of the reservoir memory used per rehearsal. This choice influences the memory complexity and the accuracy of our model. The bigger the reservoir memory, the more accurate the model becomes, but also the more resources it requires. We can see on the figures that the NI scenario is less impacted by the size of the memory than the NIC scenario. Increasing the size of the memory from 50 samples to more than 12,000 samples only increases the accuracy on the NI scenario by 2%, while it increases the accuracy on the NIC scenario by more than 35%. This table contains the performance of the proposed solution depending on the backbone used. We can see that the semi-weekly supervised learning procedure outperforms the reference training procedure by a large margin without any increase of the memory complexity or the computational complexity. While the difference of accuracy on ImageNet dataset is about 5% between the reference training procedure and the semi-weekly supervised learning procedure for ResNet 50, it's about 10% on the complex NI and NIC scenarios. Moreover, we can see that the semi-weekly supervised learning ResNet 18 is only slightly less accurate than the reference ResNet 50, while being around 2 times faster on inference and requiring 2 times less parameters. We showed that using a powerful backbone such as the one provided by Facebook AI, it is possible to design memory and computationally efficient continual learning agent with a simple logistic regression and a small rehearsal memory. In the report, you will find more detail on the hyperparameter selection and a comparison of our proposed method with different other solutions. Thank you very much.
All right, so thanks for this video that we received from the Codalab team. I guess we completed the challenge session, and I let now Massimo Caccia and Paolo Rodriguez take the reins for the Q&A session with the invited thoughts speakers. Thanks all for joining, and I'll see you all for the next edition of the challenge, hopefully.